Good morning. So as part of our research project, Motu has developed a model we call NManager to simulate different designs of nutrient regulation for Lake Rotorua. This is work we've completed in conjunction with NIWA and the model Rotorua kit just presented. That way. Some of the key questions we've been using our model to consider are what are the different costs of regulation, and can we find regulation that is most cost effective? As Hugh has already demonstrated, current nitrogen emissions for Lake Rotorua are well above the targets set by the council. And this is part of the reason for the poor water quality. We've got estimates that about less than half the land in the catchment is being actively farmed. This is responsible for almost 3/4 of the nitrogen ending up in the lake. The situation is not as dire as it might initially appear. Current nitrogen in the lake is around 600 or so. But as nitrogen moves through the groundwater, this is the groundwater lags that Kev was talking about, if we don't act now or act soon, nitrogen will move towards the current amount we're exporting, the current amount that's leaving the land. This is because of the temporal aspect of water quality. Surface water flows, such as streams, travel to the lake very quickly, while groundwater flows, the groundwater cycle that Kev was talking about, reaches the lake very slowly, over numerous years. Information about these travel times is one of the key inputs into our model. Where emissions occur is important. The spatial distribution determines how long it takes them to reach the lake. And so our model NManager uses a map produced by Rotorua, so NIWA. This is a similar map. This one's produced by GMS Science to give you a sense of what this looks like. On this map, the areas in red have very long lag times, perhaps as long as 200 years, and the areas in blue have very short lag times, less than 5 years. So there's quite a range. The other key input for our model is information as to how effectively what it will cost farmers to mitigate. And we've estimated this using a curve similar to this one. We've had an expert modeler run farming simulations. This is Duncan Smith, of representative farms under different management practices. And we've used these to estimate mitigation curves for farms in the catchment. For regulation, a dairy farm will be maximising their profit. They'll have zero mitigation and as much profit as they can have. Once regulation is introduced, the farm will mitigate. Their nitrogen, they'll mitigate, their nitrogen will decrease, and their profit will decrease as well. Initially, this will occur by changes in management practices, introducing new technology, perhaps decreasing stocking rates, but there'll still be a dairy farm, and that's what this part of the curve is intended to represent. They're still clustered around those blue data points. This can only take them so far, however. Beyond some point around here, they'll need to convert land use, and so transitioning into a less intensive land use, such as sheep and beef, or if very heavy nitrogen reductions are required, all the way down to plantation forestry. The hydrological data and some on-farm mitigation data are combined in our model, and we then use it to assess the different designs of regulation. Let's first look at how the catchment might look if we required all the farms to implement best practice. We're going to define best practice for this as no change in land use, but all farms getting down to the minimum possible leaching that our data suggests. So for the dairy farm on our previous slide, that's moving from here all the way down to here. Any further mitigation would require a change in land use. This figure gives the impact on water quality of that regulation. So the blue line is the loads, nitrogen reaching the lake. We see that in the long run, best practice is not sufficient to meet the environmental targets. This step here is the instance that we've modelled the best practice being implemented at, and while it is a significant change, it's unfortunately still not enough. This suggests that more ambitious regulation will be necessary for Lake Rotorua. Let's consider two further designs of regulation. First, land retirement. Land retirement is frequently seen as attractive because it is straightforward. The regulator picks pieces of land, negotiates sale prices, and if it's satisfactory, they purchase them and convert them to forestry, or put some form of covenant on to prevent, say, dairy farming or say agri farming, requiring them to be in a less intensive land use. And the water quality under this regulation can be determined by the amount of land that's retired each year. The other design of regulation we'll consider, compare this to, will be a trading scheme. So under this scheme, as Hugh has talked about, the regulator will set a cap, the number of allowances that are provided, and farmers will surrender allowances each year based on their emissions or their exports. And the water quality will be determined by how stringent the cap is. For the purposes of our model, we'll have kind of the following phasing, meeting this blue curve as our regulatory target. And this table gives our estimates from NManager of the net present value of the total cost of mitigation under both designs of regulation. And we're estimating the total cost of the export trading regulation to be significantly less than under land retirement, about a 20% difference. So export trading is more cost effective. Can we do even better? Kit talked about a vintage trading scheme. We asked NManager, sorry, let's take a step back. We know that the export trading scheme ignores groundwater travel times, but we would expect that if we could include this information, seeing as we have it available to us, we could potentially design more cost-effective regulation. Consider the following situation. We have two farmers. Farm 1 is far from the lake, it's at the very back of the catchment, and it takes a long time for nitrogen emissions from his property to end up in the lake. Farmer 2 is much closer to the lake. It takes a much shorter time for nitrogen emissions from farmer 2's property to reach the lake. We have fast and slow groundwater flows. If our aim is to reduce the nitrogen load in 2015, we can do this in two ways. Well, you can do combinations of these, but we'll just consider these two. Either the first farmer, farmer 1, starts mitigating in 2015, so quite early, or farmer 2 starts mitigating in 2045, quite a lot later. Obviously, if we can delay beginning mitigation for another 30 years, that mitigation will be significantly less costly. And because of this intuition, we would expect that more cost-effective regulation, or the most cost-effective regulation, would incorporate information on groundwater travel times. And we provide this information to our model. We asked it to use this to design what would be the most cost-effective regulation. And this is our result. The most cost-effective regulation, at least as we estimated for Lake Rotorua, is about 1% less costly than the export trading scheme. Why such a small gain? Here's one. This figure gives the amount of land in each land use by its distance from the lake. So here, labelled 1 and 2, this is land very close to the lake with very short lag times. And here, labelled 7 and 8, this is land very far from the lake with very long lag times. And what we see is that there's very little land close to the lake. So there's very little opportunity for us to delay mitigation at the back of the catchment and mitigate more intensively at the front of the catchment in the future. So while this diagram still holds, the farmer 2 has almost no land. So he can't do a whole lot more mitigation. So we're going to have to start mitigating with farmer 1. Hence for Rotorua. Implementing best, well, our model suggests that implementing best practice will not be sufficient. The land retirement is decidedly more costly than nutrient trading. And that the difference, because of the particular groundwater flows and the particular locations of land in the catchment, that export trading is very close to what we estimate to be the most cost-effective design and regulation.